information is brought to you by the Alco Controls Division of Emerson Electric. Controlling temperature is not a difficult thing to do. Whether we are controlling a room or a fixture, the procedure is the same. Set the temperature we wish to maintain, measure the actual temperature, and cycle the equipment to bring about the needed change. The equipment remains on until the desired temperature is achieved, and then is shut off. This on-off cycling continues, maintaining a temperature very close to the set point temperature. Control systems work with this simplicity in millions of applications. With the thermostatic expansion valve, the process is more complicated. One reason for the complexity is the fact that a TEV is not an on-off device. The TEV controls by modulating flow, not by turning it on or off. Also, we still have a set point, but we are setting superheat, a difference between two temperatures, not a single temperature. In the case of the TEV, we are controlling liquid feed to an evaporator based on the amount of superheat that is in the vapor as it leaves the evaporator. That superheat quantity is the difference between the actual temperature at the evaporator outlet and the saturation temperature of the refrigerant determined by the suction pressure. While there is no actual clear interface between solid, liquid, and vapor in an evaporator, at the inlet to the evaporator, there is mostly liquid starting to evaporate. At this point, the superheat is essentially zero. The superheat level will remain near zero until liquid is no longer present. The superheat will then increase at each point in the evaporator tubing as we get closer to the suction line. It is the superheat at the outlet that we are most interested in controlling with the TEV. To determine the superheat at the outlet, we must know two values: the temperature of the gas at the evaporator outlet and the suction pressure at the evaporator. That suction pressure will tell us the saturation temperature of the refrigerant. The difference between these two numbers is the superheat level. The great advantage of the thermostatic expansion valve is that it will measure the two things we need to determine superheat level, and then adjust flow to maintain the desired superheat. To do its job best, the TEV needs three things: an accurate source of suction pressure, an accurate measurement of outlet gas temperature, and a precise determination and setting of the superheat level we wish to maintain. With the assumption that we have an accurate measurement of suction pressure and an equally accurate reading of outlet gas temperature, let's now look at the all-important setting of the desired superheat. The first question we must answer in setting any thermostatic expansion valve is, what superheat do I want to maintain at the evaporator outlet? That question might at first seem easy. One of the reasons we use superheat is to be sure all liquid has evaporated and superheating of the refrigerant vapor has started. That suggests a very low superheat of 1 or 2 degrees would do the job. True, this low level of superheat would give us very high efficiency for our evaporator because liquid is more efficient than vapor in absorbing heat. The risk in using these low superheat levels is that as the superheat setting gets closer to zero, the higher the chances of liquid entering the suction line and flooding back to the compressor. There are some applications, low temperature as an example, where very low superheat is used. When setting these low superheats, accurate measurement at design conditions is important. Things can get just as bad at the high end of the superheat scale as they do at the low end. A superheat setting that is too high can cause a number of problems. At the top of the list is that as superheat becomes too high, the efficiency of the system goes down. Remember, a high superheat reading means not enough liquid is available to absorb the heat in changing state to a gas. We want the heat absorption in the evaporator to be done by the liquid evaporating, not by the vapor absorbing heat. The second major problem with high superheat settings is that high suction temperatures that result from high superheat cause the discharge gas temperature at the compressor to rise above safe limits. If discharge gas temperature exceeds the compressor's design limits, the system will see a loss in capacity and premature compressor failure. There are a number of ways to determine the most desirable superheat setting. The method that continues to work the best is to follow the equipment manufacturer's recommendation. He has studied the question with all system factors taken into account. If, for some reason, the manufacturer's recommendation is not available, there are general rules of thumb that can be used. Lastly, you can select a superheat setting that does the best job of cooling while at the same time keeping other critical system readings at acceptable levels. Before discussing the details of superheat measurement and adjustment, we must keep in mind the need for letting the system reach a balanced condition. It takes some amount of time for a system to stabilize after a superheat adjustment is made. System balance will normally take place in about 15 minutes. The adjustment of the superheat setting on a thermostatic expansion valve is a relative setting. This means that to make any new adjustment to the setting, you must first know the superheat resulting from the existing setting. To determine existing superheat, we need to know the saturation temperature, which can be found by measuring the suction pressure. The pressure reading should be taken with an accurate suction gauge as close to the thermal bulb as possible. The suction pressure reading should then be converted to saturation temperature with a temperature pressure chart. We also need to take a precise reading of outlet gas temperature. Notice our goal is to measure gas temperature. Since it is inconvenient and would require entering the system to measure the actual gas temperature, the temperature of the tube is more than adequate if care is taken. Be certain the measuring sensor is accurately located and insulated when necessary. This is particularly important on large diameter suction lines. We now have the two temperatures we need to determine the existing superheat in the system. If adjustment is necessary, the superheat adjustment screw is turned 1/4 of a turn at a time until the system operates with the desired superheat at the evaporator outlet. Again, be certain the system stabilizes after each adjustment to assure balanced operation. Double check that you have properly set a superheat level that will work well under all operating conditions the system will see. Let's look at the whole superheat adjustment sequence again. First, determine the desired setting. Next, measure the existing superheat. Adjust, wait for balance, and measure performance. Some hunting is inherent in all control systems. Because of time lag in the controller in both receiving inputs and in the system responding to the new conditions, the potential for hunting is always present. The effects of hunting can be reduced but never totally eliminated. A TEV that is hunting will cause excessive swings in the superheat level as well as swings in suction pressure. Where we might normally expect to see swings of 2 or 3 degrees in superheat, and we are seeing 7 or 8 degree swings, we have a TEV that is hunting. It is hunting because the rate the TEV is changing refrigerant flow does not match the needs of the evaporator. There are a number of factors that increase the effects of hunting, and they must all be considered when adjusting a TEV. In looking at alternate methods for measuring superheat, it is important to remember that no matter how measured, there are 2 values that must be known to determine superheat: saturation temperature and actual outlet gas temperature. All methods arrive at these 2 values, but by different paths. Evaporator pressure, for example, can be determined by measuring the suction pressure at the compressor service valve and then adding the pressure drop between the service valve and the bulb location. Another method, the 2-temperature method, attempts to directly measure the saturation temperature. The saturation temperature can be measured directly if the liquid-vapor interface is located and is stable. Also, there must be minimum pressure drop between the locations where the 2 temperature readings are taken. The higher the pressure drop, the greater the error in using this method. The important point is that no matter the method used, an accurate determination of saturation temperature and outlet temperature must be made. No matter how long the list of things that are controlled indirectly by a TEV, the one and only thing a TEV controls is the amount of superheat that is in the outlet vapor from the evaporator. The only absolute thing that frost on the suction line tells us is that the suction tube temperature is below the dew point and cold enough to freeze the water that is condensing on it. Adjusting the superheat on a thermostatic expansion valve only adjusts the set point of the valve. It is the temperature at the bulb, together with the suction pressure and the set point, that determines whether the valve will open or close. This relationship between suction pressure, bulb temperature, and set point is the foundation for the proper performance of any thermostatic expansion valve. System performance depends on an evaporator that is properly fed with refrigerant. The TEV is an ideal device to control the feed to an evaporator. Adjust it precisely to the correct superheat, and you will have a system whose operation will be both efficient and reliable.